I said before that we were going to be doing some more of this following the trace of execution business. So let's get to it. In this case, let's look at this function that's called count repetitions. And this function is going to be using another function called count how many. Count how many is a very simple function that basically receives a list and an element and returns how many times the element happens in the list. So it contains a very simple traversal loop for all the elements in the list. If the element is the one that I'm looking for, I just add 1 to the counter and do nothing otherwise, and then just return the count. The count repetition functions basically has another traversal loop for x in a list, and basically it counts how many times each element in my list, each of them, happens. Okay? So first here we have an example where I'm have this list 301 55 35 225, and then I run the count repetitions and get the number of times each element is repeated. 3 is repeated 2 times, 0 is repeated 1 time, 1 is repeated 1 time, 5 is repeated 1, 2, 3, 4 times, so I have it here and everywhere else that I have a 5. And with this I have successfully run my two functions, my count repetitions and count how many functions. Let's follow the trace of execution. What happens when n grows? How much does it take to run this algorithm? What's the asymptotic behavior of this algorithm? Well, basically, whenever I start running my count repetitions algorithm, I come here and have something that, as I said before, is constant, just entering a function. Then I do an assignment of an empty list to a variable which is also constant. Have a traversal loop here, which we saw was this itself is linear, because this happens once for every element in the list. So this is all of this loop, the loop itself and what's inside of it is going to take n times whatever is in here. Before we saw some loop that had something that was linear, that was constant inside of it, so all the loop ended up being linear. And we'll see what happens here. And then, sorry, we have something that's constant. So I have constant, constant, everything that's in a sequence adds to each other. So this is something constant plus the cost of this loop plus something constant. So basically, this is going to be constant and this is going to be at least linear, because the best that I can do is that this is also constant and this is going to be linear. So maybe this algorithm is linear. It depends on how long it takes to run this count how many function. Let's see it. The count how many function is here and it has a constant time declaration, as all declarations are, a header, let's call it. Then I have an assignment, which is also constant time. And here I have another loop. Okay, I have a loop that has an if and an assignment, and all of this is constant. And then I have something that's constant here too. But here, as I had in the traversal algorithm that we saw before, I have a linear time loop with something that's constant inside of it. So all of this takes linear time. All of this function, the count how many function, is a O of n function, a linear function. So let's go back to the count repetitions function. What do I have? I have something linear times something that's also linear. Okay, so I have n times n, have something that happens once for every element, and inside of it I have something that also happens once for every element. So what's going on here is happening n to the square times. And this is another type of function. Sorry, type of time complexity. When I have this type of construction where I have a nested loop with, so two nested loops, one loop with another loop inside of it, then I have this quadratic time complexity, new time complexity. Okay, we have seen algorithms whose time doesn't grow, and we call those constant when the size of data grows. Some that grow following a line, and we call those linears, and so that happens when I have a loop and something constant inside of it. And we are seeing another class now. I have a loop and I have something that's linear inside of that loop. So all of it is quadratic. And we can go and plot it like we have been doing here. Basically, we have been plotting this calls to this count repetitions function with lists that we create randomly every time, and you can see here a pretty nice quadratic tendency. So this is not a line, this is a quadratic tendency which has its spikes and so on.